Hi there, in this video we're going to have a look at doing some tan graphs from some tan functions which have one or two transformations applied to them. So if you want to, you can pause the video and have a look at all of the steps there in that top left-hand corner, or copy them down, but I'm going to get stuck straight into the example so that you can see these steps being put into place. So number one, we need to work out the period and where we're going to have to graph to and from, I suppose. So we can see that the period is equal to pi on 3, because the standard length of a period for tan is pi, and then the value of n is 3, so it's just going to be pi on 3. And then the first asymptote, which is in step 2, is worked out by halving the period. So a half times pi on 3, which is equal to pi on 6. So where does that asymptote go? Okay, well, we need to look at the phase shift. There's no phase shift here, which means that effectively the center of our graph will be at 0, 0, and then it'll be continuing on based upon our period from there. So we can kind of start at 0 and say that our next asymptote is going to be at pi on 6. So I'm going to draw that in now, and I'll just put it in as a different color so it stands out. Draw it in red. So just copying that down like so. And because of this, all these dotted lines here, I'm just going to put pi on 6 on top here, just so it's a bit more clear, I suppose. So there's our first asymptotic line. And then every other asymptote is going to be pi on 3 onwards, okay, or backwards. So the next one would be pi on 3 here, so that's the period length, pi on 3 further. That's pi on 6 plus 2 pi on 6. That's 3 pi on 6. It happens to be pi on 2. Do I do another one after that? The answer is no, we don't do another one after that, because the domain finishes at pi on 2. Easy as that. Now, if we go back pi on 3, well, that'll be 1 pi on 6 plus another pi on 6. So effectively, we're just going to have the same length here. Trying to keep it nice and even. I probably won't. I'll probably have a fail there as well. So that's negative pi on 6, and go back another pi on 3, now full period back, and that'll get me to pi on 2, or negative pi on 2, really. So there's my other asymptote. Right, so I've got my asymptotes drawn in. What next? Okay, we draw them in. So we can see that there's a negative in front of tan of 3x there. So instead of going upways from the center, we're going to go downways. So, I mean, I just tend to just do one bit at a time, like I do with the sine graphs. Do one curve that goes down like that, then another curve that goes up like so. And then do the same thing here, pick the center between these two, and do one curve that goes up, and one curve that goes down. And then pick a center here as well, and goes one curve up and one curve down. I guess I should label those x-intercepts, shouldn't I? So that's what I'll do. So the x-intercepts are going to be halfway between these two. So what's the halfway point between minus pi on 6 and negative pi on 2? Well, that's negative 3 pi on 6. That's negative pi on 6. So in between is going to be negative 2 pi on 6, otherwise known as, I'll zoom in so you can see a bit better, otherwise known as negative pi on 3. So there's going to be a negative pi on 3 there. And with a similar logic between pi on 6 and pi on 2, we have positive pi on 3. So we've got all of our x-intercepts drawn in, and job is done. However, there is one last thing that we need to consider, and that is that this graph as it stands now has no sense of scale. So I should be able to look at a graph without this bit at the top here and be able to work out the function if necessary. And I can't. There's nothing here that allows me to. So I need to work out the scale. I need to go to the next page to show you this. So in some circumstances, you may need to calculate one other point for scale. The easiest point is found here. The tan of whatever the argument of tan is and whatever makes the x component equal to pi on 4. So the argument equal to pi on 4. And why is that? Well, I'll leave you to think about it. You might want to pause the video and think. By the way, what are the circumstances? The circumstances is when the y-intercept is 0, 0. If the y-intercept is anything else, then that y-intercept will give you the scale that you need. Okay, so working out that extra point at x equals what? Well, when we have, what we do first of all is we take the argument to tan, in this case 3x, set it equal to pi on 4, and work it out. So that means that x is equal to pi on 12. Great. So now we can finish off at x equal to pi on 12. What do we have? Y equals minus tan of 3 times pi on 12, which will give me pi on 4. Aha, maybe that's telling you why we do it, which is equal to negative 1. So we deliberately choose, we could choose any value we want to for scale, but by picking a coordinate for x, which makes this tan of pi on 4, well, the tan of pi on 4 is 1. You can look at your charts for that, or you can do your little triangle. Because it gives us a value of 1, it makes working out the y coordinates super easy. So when x equals pi on 12, y equals negative 1. So I can go back to my graph, and I'm just choosing a different color so it stands out. I can go down to, I can go to pi on 12, and which is going to be right in the middle here. Between here and here will be pi on 12, and then I'm going to go down to negative 1, so that's going to be about there. I'm going to put the coordinate in. It's going to be hard to see when it's all zoomed out. It looks like this if I zoom in, and that'll be pi on 12 comma negative 1. Okay, so the graph ends up looking like this with a lovely scale.